Welcome, everyone. We're going to talk about parametric equations. What are parametric equations right here? And if you might want to grab your calculator out, because we're going to do this. Her Wi-Fi is slow, and why she's not here, no problem. I'll record this. You'll get it later. So if I asked you to graph the equation, I'm going to do this on my calculator right here. If I asked you to graph the equation, I'm going to clear this one. We're going to graph x squared. What does it look like on a calculator? So I go to graph. And it looks like a parabola, right? We've done this before. And so here's the picture right here. Here's it on a calculator. And if you have x values, like this as a table, you'd plug in certain x values and you get certain y values, right? Oops, that's a 1. 2 would be 4. 3 is 9. -2 is like -4. And this is what you're used to for graphing, right? So that's a normal equation. Normal stuff. Now, parametric equations are the idea is I'm using two equations to build one graph, but I'm basing it off a third variable. I'm basing it off a t, which stands for time. So I'm going to graph these two equations, x equals t and y equals t squared. Now, if you're on a graphing calculator, you have to switch this to parametric mode. Oh my gosh, talk outside. So hit the mode button right here and switch from func to par right here. So when you do this, and now I go to the y equals, notice there's x1 and y1, x2, y2. So it's a pair of an x. So basically I have an equation for my x values, an equation for my y values, and we move over time. So x is going to be t, and y is going to be t squared. And watch what happens when we graph this. It moved up just like this. So the idea with parametrics is we're going to start maybe like time equals 0. What ends up happening is we're going to graph based off this. So when t is 0, both of these are going to be 0 and 0 squared. When t is 1, x will be 1 and y will be 1 squared, or 1. When t is 2, x will be 2 and y will be 2 squared, 4. And when t is 3, it's going to be 3 squared, 9, and 4, and this will be 16. So what ends up happening when I plot this is I start here, and I maybe go to 1, 1, and I go to 2, 4, and 3, 2, and so on. It's actually moving in this direction. Well, what's a neat thing? You'll notice, and I'm putting these arrows on here, because parametrics, it's not just what it looks like, but it's like how it travels. So it's, and one thing you might notice here is this is like just the left half of a parabola. And it's traveling this distance right here. It's just starting at 0 and going on from there. So it's not just the shape, but it also gives you how it moves over time. Like with the normal graph, it just exists at once. I know the calculator draws it, but that's kind of how it works. Other neat things when I do this, I can change. Now, I'm going to change a few things. What if you didn't start at 0 and I counted up, right? Like, I'm going to actually do it again. What if I don't start at 0? What if I start at like -2? If you start at -2, this will be -2, and this will be +4. -1, I'm just gonna do integers. This would be just -1 and be +1, 1 squared. 0, 0, 0, 0, 1, 1, 1, 2, 2, 4. So if you plotted those, you'd start seeing the shape. Let's say -2, 4 would be here. -1, -1 would be here. Oh, this should be -1, 1, 0, 0. You would see plots like this. You'd actually see it doing this kind of shape, but it started not from 0. I started out here at -2. Watch what that would look like on a calculator here. So I'm actually going to go to, I think, format. I think I go second. I think it's called, actually, is it called window? Yeah, it's window. So you hit window on here. So you can set your T min and T max. What if I set my T minimum? That's where I start to -2. I set the T maximum. I'm going to set this maximum to 2. And just keep the same T steps. Who cares? And I'm going to say graph. Okay, that was super quick. Actually, I'm going to zoom. I have to zoom standard. I've been zoomed in way too much. So what if I set this again to -2 and this one a +2? I graphed it. Notice it started here and then it went up, but it goes super fast, right? I could even change this. What if I started at -5 and went to 2? it'll start at a different part. So it's still forming this parabola shape. What if I went from -5 to like +5? It'll look like that same parabola shape we had before, but it just changes where I start and where I end. Other neat things, like what if I changed, if I did 5 and -5, would that reverse it? No, it's going to cry. How do I, okay, so you might ask, like, how do you reverse the movement? And you can, and we'll talk about that. Actually, how would you reverse that movement? So here's a crazy thing. If I were to change this from t, what if I change this to -t? Watch what happens when I graph this. Backwards. It still draws the same shape. So parametric equations, they're still giving you the kind of, it's the shape of the parabola or whatever. We can form a shape like normal, but the parametric part like shows you how it's created over time, I would say for that. So another way to say this is rectangular equations tell you where the graph exists. Like that's what you're used to. Cartesian, you might hear Cartesian as a word, and I'll write that out here. Cartesian, I think that's how you spell it. But rectangular equations, that means you're like x, y only. They tell you where the graph exists. You just draw it at once. But parametrics tell you where and when. So the where is the x and the y part, but the when is the t part. So, and you're going to need this if we start talking like physics. Maybe we talk about movement. We might use this to track movement right here. Maybe we want to know where a point is at a certain point in time. Or maybe we just need to add a third variable for a set of equations. So a lot of times though, it's movement. And a lot of times in this class, if it's for any real life thing, it's some physics type problem. All right. So parametrics, we use a combination. Now, so a little bit more about plotting these, and we're not even into the calculus yet, are we? So what if I have these two equations? X is t squared minus 5 and y is t over 2. So let's just plot this as a table. I want to show you what it looks like. So let's say I started, and let's say my range is -3 to +2. I'm just going to go by integers. So okay, so let's do the y values. Y is just cutting everything in half. So y is half of this, so negative, I'm going to say 1.5. I'm going to do decimals. Half of this is -1. This is -0.5, 0. This will be 0.5, and this is going to be 1. Those are the y values. Now let's try the x values. It's t squared minus 5, so it'll be 9 minus 5, so it's 4. This will be 4 minus 5, so -1. This will be 1 minus 5, -4. It'll be just -5. This will be -4. And this will be -1. So now we got these pairs, we're going to have to plot them. So I'm going to plot them. My first point. Wait, was that +4? That's -4. -4. So my first, wait, that's not -4, that's +4. My bad. Okay, that is +4. The first point is x is +4, y is -1.5. It'll be this point. And then it goes -1, -1. So -1, -1. I'm going to just draw a line going there too. Connect it. I'm just going to put an arrow kind of indicating it's going that direction. Next one's -4 and then -0.5. And then I'm going a line going this direction. -5, 0. It's kind of curving up. -4, +0.5 might be here. So it looks like it's curving back. And then -1, +1 would be right here. So it goes to here. And there we go. So that's how those would travel. Now, if you want to see this, what it looks like in a graph here, I'm going to do this for funsies just to show you. Squared oops. Oh, geez. Delete. -5. And this is going to be t divided by 2. And let's set the window. So I want to change the range from -3, +2. Steps, I don't care what the steps are. And it still makes that same shape. So, and you can zoom it if you want to see it better. But if I zoom in, I'm going to choose zoom in. Okay, that didn't help very well. But there you go. You get the idea. Right? Still forming that same shape. That's how parametrics work. You can build the shape. You have movement over time. There it goes. All right. So I don't want to plot more. Who cares? I could plot more of these, but who cares right now? I could ask you to like change it from rectangular to regular form. This is where like you're combining these. I don't think that's ever asked in calculus. This is kind of some pre-calc type stuff. If I wanted to combine these two, basically like you could rearrange this x to solve this equation to solve for t, and then you substitute in. But I don't want to do that. Same thing here. I mean, we could do this with cosines and sines. Too much work. Well, let's talk about deriving it. Let's do the calculus parts of this. You can also derive these. Like, how do I find the slope? You know, like if I had the equation y equals x squared, and I wanted to find dy over dx, it's just be 2x, right? But how do you do dy dx and I have two parametric equations? So let's say, for example, I had my two parametric equations where x equals t and y equals t squared like I had before. Good luck. Pass the AP Art test, but also pass my test too, please. Now, how do you do it when you have parametric equations? Do you have to combine them and turn it into this first? No. What you're going to do is it's the derivative, the dy dx for parametrics is derivative of y divided by the derivative of the x. So one way I like writing that is it's like basically dy over dt over dx over dt. So think about it as like, oh, I took these and put like over dt on both sides. So we're just deriving each of these things with respect to t. And you divide the y divided by the x, this gets you it, all right? So for example, the dy dt for this case would be the derivative with respect to t of the y term, so t squared, over the derivative, just writing it like this, of the x one. So it would be 2x, 2t on top, and just 1 on bottom. Or another way of saying that is 2t. That's how I derive with parametric equations. Derivative of the y divided by derivative of the x. All right? So, like, you just got to derive each of them, divide them. Hopefully that's pretty, not too bad. So let's say if I wanted to find, I'm going to go back to an old equation. Let's say if I had these two equations, x and y right here, and I said find dy dx. Okay. So I would have to say, well, dy dt is derivative of this 3 sine of 0, which so would be 3 times cosine of theta. That's the derivative of that. And then I'd say, well, the derivative of x, dx dt, derivative of cosine is negative sine theta. So then my dy over dx would be 3 cosine of theta divided by negative sine of theta. Done. Oh, it says, I said theta. I mean, or t. I should have said t. Whatever. So used to using theta is what I deal with. Okay, so in this case, they use theta. That's what that, so I say theta if you don't know that word. Theta. That's that. Usually when we're talking radians or degrees, we use theta sign. So you could do parametric. Typically, when we're doing that, it's polars, but they're treating it like parametric equations for this case because it's big stuff. Same idea. All right, so here's the weird thing. The second derivative is the weird one to remember. Okay, that's the first derivative, dy dx. Well, how do you do the second derivative? And you would think, oh, just derive it again, right? That's how you do a second derivative. Well, you can't just derive it again because we're doing this dy dx thing. So here's the real formula for it. And you look at that and you're like, what the heck is that? So here's my rules. You have to derive dy dx again, that's on top. And it's divided by another dx dt on bottom. So you derive it a second time, but you also have to divide it by the dx dt, the derivative of the x part. You might be like, well, why do you have to do that? It's because basically when you do a second derivative of the old one, you're doing this thing. You're doing another one of these. And technically we're dividing by the divided by dt on everything. So dx divided by dx dt is the old derivative of x. But a d over dt just means, hey, derive that thing inside. So you're deriving the thing again, but then divide it by a dx dt. Like, this looks really confusing. I remember it this way. Derive it by dy dx again on top. Just derive that original thing. Derive the original thing. Oh, no, you derive it by dt and then divide it by another dx dt. All right, so let's show you what that really looks like. Let's take this example. These are different than what I just had. We're going to find dy dx and dx and then the second derivative. So dy dx. So my dy dt is going to be 3 cosine. Oh, this is actually what we just did, right? 3 cosine of t. And then my dx dt is going to be negative sine of t, right? So then my dy dx is just those divided. So it's going to be 3 cosine of t divided by negative sine of t. So yay, that's the first one. Okay, now to find the second derivative. Okay, so what I have to do is I have to derive this guy. I have to derive this one with respect to t. I can put that negative on. Okay, oops, don't want to say equal. I want to derive this whole thing. I'm going to put the negative on top. So there's a few different ways you can do this. Maybe you just want to do this by quotient rule right here. Let's do it by quotient rule. So by quotient rule, I can say this is negative 3 cosine of t, so it'll be f prime, so it'll be positive 3 sine of t times the bottom, another sine of t, minus this thing, negative 3 cosine of t, times the derivative of this, cosine of t, all over the bottom squared. That's the derivative of this. And then we have to divide it by another one of these. So my final answer would be this thing, and then just divided by negative sine of t. You can say, oh, that's my answer. I mean, if that's all you need to do and you need to simplify, you're done. If you wanted to simplify this, I'm just going to do this. On the top, we have 3 sine squared of t, if I combine those, plus 3 cosine squared of t. And on the bottom, I'd have negative sine cubed of t. Now, there's a Pythagorean identity. I don't know if you remember this. Sine squared plus cosine squared of whatever. Remember what this equals? Equals 1, right? So I can actually rewrite this as 3 times. You can factor out the 3. So on the top here, we're just left with 3. 3 times 1. And the bottom, I have negative sine cubed of t. And if you wanted to write that differently, you could actually write that as, 1 over sine is the same thing as negative 3. It's cosecant of t. Or cosecant cubed. Or something. Now, you might be like, wow, that was a lot of work to simplify that. I want to show you something else. What if you did this differently? So if you know your trig stuff, you can simplify your life a little bit. You can take this equation right here. I'm going to rewrite this and say my dy dx. Cosine over sine is cotangent. That's like the inverse of tangent, right? Or the reciprocal of tangent. So it's actually negative 3 cotangent of t. So if I just say negative 3, what's the derivative of cotangent? It's cosecant squared, or negative cosecant squared, right? So the derivative of this dy dx would be negative 3 times negative cosecant squared of t. So which is 3 cosecant squared t. And then you divide it by another negative sine of t, and you'll end up getting this answer, because you'll end up getting, 3 cosecant squared of t divided by negative sine of t, which is the same thing as this with another cosecant if you wanted to. I show you that just as a way you didn't have to use quotient rule. You could have said, hey, it's cotangent. Maybe the math would have been easier for you. Or you do, like this answer right here is the same as this answer. That's your trig for you. All right. Other things that you might have to do, we can still apply things like find the slope and concavity at a point. And I think this is a good one to do right here. So if I wanted to find the slope, let's see, so slope at the point 2, 3. So this is like the x and y value still, but now I have parametric equations. You might be like, well, what do I do? In these parametric equations, well, to find the slope at that point, okay, so slope is just, so let's go back. Slope is just the derivative at that point. So it's dy dx, but at that point 2, 3, right? Or at the point usually when x equals 2, how they usually say it. But we're different. We're parametric equations here. So dy dx is just equal to dy dt over dx dt, right? Okay, so what does dy dt equal? The derivative of this top thing is going to be, so it's going to be 1/4 times 2t, or it's going to be t over 2 on top. Y prime is t over 2. And the derivative of this thing, square root of t, is going to be 1/2 square root of t. That looks super gross. So I'm going to rewrite that as t over 2 times the reciprocal 2 square root of t, 2 square root of t over 1. Those 2's cancel out. And we're left with t. This is like t times t to the 1/2 power. It's actually t to the 3/2 power. Didn't write that very well. T, I like doing cursive t's. T to the 3/2 power. So that's my slope formula, dy dx. But now you got to plug in the 0.23. And you're like, wait a minute. What do I plug in for t? This is x and y. So you have to do the step of figure out what t is. Well, if you know that x is 2, I can just substitute this 2 in for x. Say 2 equals square root of t, or t has to equal 4. So you have to like plug those in. Now you could have also plugged in the y value and said 3 equals 1/4 t squared minus 1. You'd add 1, you get 4 equals 1/4 t squared. You multiply by 4, 16 equals t squared. If you square root both sides, you get t equals 4. Or t is technically plus or minus 4, because negative 4 would work. However, they tell you t has to be greater than 0. So it's positive 4. So the neat thing is you don't have to check both numbers. You can just check x or y in these cases to find your t. So to find the actual slope, your m is going to be 4 to the 3/2 power. Is 4 to the 3/2 power. Which to simplify, if you don't know how to simplify that, that's like the square root of 4 cubed is 2 cubed, which is 8. Remember how to do that. So 8. That is the slope at that point is 8. My final answer. Now, concavity. Can find the slope in concavity at the point. So concave up, this is related to second derivative. So we got to find the second derivative. So d squared y over dx squared is going to be the derivative of this thing, the original, derive this again, 3/2 t to the 1/2 power over the dx dt again, over 1/2 to the square root of t. That's super gross. I'm going to change colors. So it's going to be 3 over 3t to the 1/2 power over 2 times the reciprocal of this thing, it's 2 square root of t over 1. Well, those 2's are going to cancel. Oops, I tried to do red. And t to the 1/2, and this is t to the 1/2, so that's going to be 3 just times t to the 1. So it's 3t. 3t is my second derivative. Now, at that point, when t equals 4 still, so when t equals 4, that should be, so d squared y, dx squared, when t equals 4, should be 3 times 4, or 12. Since our second derivative is positive, we are concave up, smiley face. So I'm going to say it's concave up, because the second derivative is positive. There you go. That's basics of all this. I showed you an example of what you can do with concavity, with slope. I mean, we could do increasing, decreasing, but we're using parametrics. I think the key things to remember right here, I don't even need to do more examples on here. Tangent line, it's all the same stuff we've done before. The key things to remember is to find the derivative with parametrics, the derivative of the y divided by derivative of the x. And then the second derivative is derive the dy dx again, but then you also have to divide by another dx dt. This is the part people forget. They can derive it again and say, oh, it's second derivative, just derive it again. You've done this forever. Then they forget the dy dx over dt. Yep. Now, I mean, the other parts to this is sometimes you have to figure out what t is because I substituted a few things, like in this problem. They told you x and y, but they didn't tell you t. You kind of had to do a little bit of math there. Don't just assume the x value. That would be the trap. But there you go. That's parametrics for you. I threw some stuff on Khan Academy. Try that out. Do some more practice later too. That's it for my video.